All right. Good afternoon, everybody. Welcome to the second lecture of the Statistical Foundation in Reinforcement Learning. Can you guys hear me okay? And also, can you guys see the share screen? All right. Today we're going to continue with Markov decision processes. There might still be more people to join, but I'll start the lecture and then we'll start from the recap. So we'll have just pick up our memory from Monday and what we have learned from Monday, and I'm gonna just quickly summarize that what we learned before we move into the new topics. All right. So we started to talk about Markov decision processes. So what are Markov decision processes? So these are a set of models parameterized by this tuple of 6 elements that describes the underlying environment that this reinforcement learning agent operates in. So we have the state space, the action space, the transition probabilities, the reward vector, so the expected reward function, the discounting parameter gamma. So gamma is typically between 0 and 1. At 0, then this is a completely myopic planning. You are doing basically greedy strategy to optimize your immediate reward. When you are at 1, then the cumulative reward might not even be well defined. So we typically choose this discounting factor to be, say, 0.99, so that we can plan ahead for an essential horizon of roughly on the order of 1/1 minus gamma. And this is because when we add up the 1 plus gamma square plus all the way to infinity, this is what we got from the geometric series. Okay, and the transition kernel's output, so we're using this notation to denote the probability distribution supported on the state space, and the reward, the expected reward we assume is bounded. Right? So without loss of generality, we can assume it's bounded between 0 and 1. Okay, and lastly, there's the initial state distribution mu0, as we talked about last time. So when we run a particular policy, so these parameters describe the joint distribution of the sequence of state action reward triplets as a sequence rolls out all the way to the end of the world. So we use a capital letter S1, A1, R1 to denote the state action reward in terms of its random variable, and then transition to S2, A2, R2, and so on and so forth. So we call the whole thing the history and the entire transcript of the trajectory. We call this a sequence of random variables the trajectory that we rolled out. Okay, so the S1 is drawn from mu0. And A1 is taken by A1 is drawn from taking a particular policy of the say it's a stationary policy. Then this is drawn from this distribution given given S equal to S1. Okay, and then S2 is drawn from the transition kernel of S given S1 to be the realized value and A1 to be the chosen action. All right. So that's the setting. I hope everybody still remember it. Now we define how do we evaluate a particular policy. So the immediate reward function. So typically, like in the previous definition, we parameterize it with only S and A, but sometimes there are also dependence on the next next state that it transitions into. So the differences of these two almost equivalent definitions are very minor. So for now, we're gonna like use it in interchangeably. And without loss of generality, you should consider like the reward function, the expected reward function doesn't really depend on the next state. On the other hand, if you want to also get rid of this variable a, then you have to consider the expected reward of a particular policy pi. Then in which case we use the superscript pi to add to this r function, and this gives us r pi at state s, right, defined with this conditional expectation. Right, so in general, when we have this pi that's on this superscript, it denotes that function depends on the particular choice of the policy that you play. All right, and we define the value function. So value function, so this is a scalar. So expected immediate reward is a scalar, and the state value function is a function supported on the state. So in the discrete state case, this is a vector. This is a vector of length, the cardinality of the state space, and it is defined from the first principle by the expected value of the sum of the cumulative reward, discounted cumulative reward when you start at initial state s. State action value function says that when you start at state s and action a, then you roll out with policy pi, right? And then the total sequence of reward, and then you take expectation, gives you the q pi function, right? So with this definition, we're not restricting on what this policy pi could be. It could be the fully general policy, could also be stationary policy and deterministic policy. That the definition itself is fully general. So what is the goal of Markov decision processes? As we talked about, the MDP describes the environment, and the inference problem in after knowing this environment is to plan ahead of time for a strategic sequence of actions and then try to maximize the expected reward. Right, so that's called the MDP planning problem. And to put it differently, it is about finding the optimal policy pi, right? So we can define the optimal value function v star and q star in this way by maximizing the v pi at every s, and then we hope to find the optimal corresponding policy. It is unclear a priori that why this optimization problem necessarily why this problem necessarily has a solution that applies to all coordinate s simultaneously with the same I guess policy. It's not clear from here, but we proved last time that there actually exists a stationary policy that simultaneously maximizes v star for all s. Okay, so this goal is well defined, right? So the task for finding an optimal policy is to find the pi star such that the value of the value function of that pi, I guess the pi star is the same as the optimal value function for all state at the same time. And sometimes for computational reasons, we wanted to solve the approximate version of the problem. So we say that pi is epsilon optimal if the L infinity norm between this v pi and v star is bounded by a parameter epsilon. Okay, so we want this v pi to approximate v star uniformly at all coordinates by parameter epsilon. So I hope these are clear and familiar to you. So last time we talked about 3 different function classes, starting from the fully general function class, policy class that could take the entire trajectory. So of S, state action reward triplet to the power of unspecified length, together with the current reward, and then output a distribution of the action. Then there are like simpler policy classes like stationary policy and stationary deterministic policy classes, which depends only on the current state, right? So stationary like is like highly overloaded words. So in the context of reinforcement learning, this usually refer to stationarity usually refers to memoryless. Yeah, so you can already see that this is a natural family of policies that are coming from the Markovian properties of the Markov decision processes in the first place. Because all the future rewards and future distributions are completely described by the current state. And since they are independent to things that happened before, so what we've proven last time is essentially essentially to leverage Markov's property and prove that the station it suffices to consider only the stationary policies. Okay, so that's what we spend most of our time on. It suffices to consider the stationary policy. So let me quickly remind you guys what the arguments were, because during the proof, it's not only the proof for this proposition, but also it introduces several interesting ideas and interpretations of the problem of MDP planning to begin with. So first of all, the key idea is the so-called occupancy measure. So the occupancy measure, which we denote as nu pi, when the initial distribution is mu. So nu pi of S is defined to be the summation of t from 1 to infinity, so gamma to the power of t minus 1, and then we got the I guess the marginal probability distribution. So the marginal probability distribution on the pi of this random variable S t is equal to S. Okay, so think about this is d pi. So I used the capital P in the last lecture, but this is like another standard notation. So I guess the people often say that the most difficult part of Markov decision processes of reinforcement learning is the issue that there are so many notations to keep track of, and we don't have nearly enough Greek letters to work on. Yeah, so there's a question regarding this proposition in the chat. So Ari asked about, does it suffice to consider stationary policies on both the infinite horizon and finite horizon settings? Yeah, that's an excellent question. So we didn't talk about the finite horizon episodic setting yet. We will be talking about that in the future lectures. So the short answer is that for finite horizon settings, the optimal policy is no longer stationary. So it depends on the time steps, and actually the value functions are also time dependent. So in general, like you need to consider non-stationary policies in a finite horizon setting, even if the state transitions themselves are stationary. Okay, so we'll see more of that in future lectures, but for now, let's consider infinite horizon discounted setting. Okay, so now we have this occupancy measure defined as the state. We can also define the state action occupancy measure. Okay, so the state action occupancy measure is again the sum of this t minus 1 and d pi. St equals to S, At equals to A, right? So this is a so-called state action occupancy measure. So what does it say? So these d pi are the marginal distributions under the policy pi that at time t you are observing state S. Right? Similarly, so d pi Sa is also the marginal distribution that you observe Sa pairs at time t. Right. So now I'm summing them up, but with a discounting factor in front. Right. So this is essentially capturing the essential occupancy in terms of its effect on collecting the reward, on how likely am I gonna gonna see state S or state S action A pairs throughout the entire infinite trajectory of the MDP. Okay, so that's the intuition behind occupancy measure. We derive this by like through a different way, which essentially says that the value function of pi can be rewritten as the inner product of the occupancy measure of S, actually SA, mu SA and R of SA, right? So this is saying that since the expected reward, whenever you run into this state action pair, this is expected reward that you get, right? It suffices to multiply this with occupancy measure and then sum everything up and sum over S and A, and that gives you that gives you the policy of this the value of this policy pi when the initial distribution is mu. Okay, so with this, the idea of our proof to say that if there is a policy that is optimal, or for any policy that's non-stationary, there always exists a policy pi prime which is stationary, such that the new pi SA is equal to the new pi prime S and A, right? And that tells us that it suffices to consider it suffices to only consider stationary policies, because for any policies that are non-stationary, there's another policy that gives you exactly the same value, exactly the same value. Okay, so I hope that explains the occupancy measures a little bit more. And then we after proving this, we apply this proposition to show that there exists stationary policies that is optimal, and that proof is more understandable. So basically we can construct a non-stationary policy that is optimal by appealing to the definition of V star and Q star. And then we can apply this proposition to convert that into a stationary policy, which happens to have exactly the same value. All right. Okay, and then towards the end of the last lecture, we got to the part of Bellman equations. So these are the fundamental equations of Markov decision processes and reinforcement learning. And for stationary distributions, things are quite nice. And when we restrict ourselves to stationary policies, when we restrict to stationary policies, we can define the v pi function. So this is a value function on the pi recursively using this using this formula, right? So this is taking expectation over A drawn from pi AS, and this summation is taking the expectation over the system transition S prime drawn from P S and A, right? And then once we have that, we are basically adding. So what does this part say? This is the immediate reward, the expected immediate reward that you get. And how about this? This part is a discounted future reward on the pi on the pi. And the fact is that now that the value functions, the policies are stationary, and the future reward are like starting from S prime at location at time 1 is equivalent to starting from S prime at time step 2 or time step 3. So it doesn't really matter when you start, as long as you see this this state variable as S, then everything's going to happen. In expectation is exactly the same. So for stationary policy, this gives rise to this very nice looking Bellman equations. Okay, so I leave this as an exercise to prove this. using the stationarity and using the first principle definition of V pi. I'm not sure if you guys have done anything related to that, but I'll teach you how to derive it in the next slide. But before we go there, I wanted to point out that typically there are many versions of Bellman equations. You can write it exclusively with respect to using V pi. You can also write it exclusively using Q pi. And alternatively, you can somehow combine V pi and Q pi and then write write the Bellman equations accordingly. For instance, the equation above, right? So what this is saying that if we strip out the expectation at the very end, so everything that's written here inside the first expectation over A will be the same as Q, S, and A. So that's what the last inequality is about. So similarly, we can write this Q function to be summation of S prime P of S prime S and A, and I guess R of S A S prime. So when it doesn't depend on S prime, you can simply take this R S A out of this summation, and plus well, gamma. So in place of this V pi, we can now just decompose it into sum of A prime pi A prime S prime, and then Q pi S prime A prime, and that's it, right? And this is the same as the V pi function at S prime. Right, so notice that this equation contains only Q pi. So sometimes it's more convenient to use the Bellman equations for Q functions. Sometimes, other times it's more convenient to use the Bellman equations with respect to the V functions. Now, so let me quickly derive the Bellman equation for you, because it'll reuse the trick that we talked about last time when deriving the occupancy measure. So let's derive the version of the Bellman equations for the V function, and then I'll leave it as an exercise for you to do the same, maybe from the first principle for the Q functions as well. So by definition, V pi is equal to summation of t from 1 to infinity, discounting factor t minus 1, and then the reward of st and at, given S1 is equal to S, right? So that's by definition how this V pi function is defined. And now let's strip out the first item as before. So let's strip out the case for t is equal to 1. So we get E of pi R of S1 and A1, S1 and A1, and conditioning on S1 is equal to S. And then we are adding the remainder pi summation of t from 2 to infinity gamma t minus 1 r of st at r of cat I guess given that S1 is equal to S. Okay, so what is the first term? The first term is basically R pi of S, right? So now we'll do this typical thing of change of change of variable by defining this t tilde to be t minus 1, and then we can rewrite this summation, and actually after we extract a factor of gamma out, and this becomes the E pi summation of t tilde from 1 to infinity gamma t tilde minus 1. So notice that I've already extracted one factor of gamma out. So you will have you have this instead. So notice that previously you were summing from t to from 2. Now we're summing from 1, but the indices are exactly the same. So I will have as t prime AT prime. Yeah, I think I've missed something here. I think I've missed the summation. So I need to sum over the P under pi, the transition into S2 equals to S prime and S1 equals to S, right? So I need to do this and sum over S2 here and put this here. And now once I do that, this becomes S2 equals to S prime. Let me just rewrite everything that's here. So summation of S2 P pi S2 equals to S prime, S1 equals to S. This is S. And then conditional expectation of sum from T tilde from 1 to infinity gamma T tilde minus 1 R of ST tilde AT tilde given ST. So previously this is S2. Now this becomes S1, right? Because I'm changing this this T to be T tilde equals to S prime. All right. So now notice that by stationarity I can replace this whole thing with the same value function, because notice that this has exactly the same form of that. And with stationarity, starting from the second step at state S prime is the same as starting from the first step at S prime. So by the stationarity of the policy, I can rewrite this as R pi plus gamma sum over S2 P pi S2 equals to S prime, S1 equals to S, and then V pi and S prime. Okay, and that's a Bellman equation from the previous page. So the only thing that I didn't tell you about is what is this P pi, right? So recall that P is a transition dynamics of S and A, right? So P pi is really is really just marginalized over this A. So P pi of S prime and S is equal to this by the Bayes rule, and I'm applying this policy A and then sum over A, right? So to this get rid of this A factor, you can think about this as so in matrix notation. So this is R S by S, and this is R S by SA, and then essentially we're marginalize out this action parameter. Okay, so I hope everything makes sense for now. So we can also write this Bellman equations in a simple matrix form where we represent this V pi to be a vector. So let's say V pi is now a vector in R to the S. So V pi is equal to R pi, which is also a vector in the same dimension, and plus gamma, and then we have this P pi function multiply with V pi itself. So this P pi matrix now is the I guess the transpose of this transition matrix. So this P pi matrix is in R S by S, but it is the input is S prime. So it's really the transpose of the transition matrix on the pi. Okay, so this is by convention. So you can equivalently call this P pi to be the transition matrix and add a transpose on top. But this is a standard notation to use where the input is so this is like the backup operator. So I'm backing up from future state to the parent state. So this is S, this is S prime, as it is parameterized. Therefore, you can write this in the very nicely looking and simple matrix equation. Yeah.
I just
yes.
want to make a short comment. So for the second equal sign, you are essentially using like the law of total expectation, right?
Yes, yes, yes,
yeah,
exactly. So by writing down the second part,
clearly,
right. So I'm using, excellent point. I'm using the law of total expectation, which says that E of X is equal to E of E of X given Y, right? Yeah, so this is the law of total expectation. There's a homework question related to this in homework 0. So we're going to be using law of total expectation and the law of total variance a lot in this course. Okay, so any questions regarding this proof? Good. Okay, so like I said, there are various different forms of Bellman equations. So when the policies are stationary, things are nice, and you can relate the V function and Q function in this way by this notation, and especially for stationary for non-deterministic policy. What I really mean is that this is the expected value of Q pi S and A when A is drawn from pi A given S, right? So this is just a shorthand for this more complex notation. And clearly, so this is equivalent to what we've just proven just now. So what I wanted to say is that this matrices forms actually is quite nice, because then you can actually work out the closed form solution for these values. Say the first equation. It is the same as if you group the V pi vectors together, you get I minus gamma of P pi times V pi is equal to R pi, right? You can solve for V pi by just solving a linear system of equations. And similarly, if we look at this Bellman equation for the Q function, then you also get I minus gamma P pi. And Q pi is equal to R itself. So this R is in R to the S, this R is in R to the SA, right? So I'm overloading the notation. So mostly this is to avoid the clutter. So this P pi is a matrix of R SA by SA. And this P pi is R S by S. They both depend on pi, but they depend on the pi in slightly different ways. So maybe a better notation would be to add a tilde here. But yeah, so it's it makes the mathematics much harder to read. So I tend to just keep it as P pi, and then the dimensionality of it will be clear from context. Right. So this is created by marginalization. Marginalized over A, and this is created by a joint over A prime, right? So it becomes SA by SA matrix. Okay, so I've already told you that you can solve this by solving a linear system of equation, right? And so on. So what makes it very interesting is when we connect this with the occupancy measure that we talked about just now, right? So recall what is occupancy measure? Occupancy measure says that the value of this policy is equal to, the inner product, so the sum over S and A, R of SA, and then the occupancy measure of S and A, pi on the mu, right? So this is a inner product of R and mu pi for policy pi under the initial distribution mu, right? So what we described last time was that there is actually also a Bellman equation that holds for these occupancy measures. Okay, so this is what I'm gonna write down. So the occupancy measures, we've learned that the state occupancy measures satisfy this equation, mu of S plus gamma sum over S prime and mu of pi S prime and P pi S prime. So this is the transition from S prime to S, where S prime is the state that could have getting you this state. So it goes towards the other direction, but this has a very similar form to the corresponding Bellman equations for value functions, for the V functions and Q functions, right? So we can also write the same thing for the state action occupancy measure. State action occupancy measure SA. This is so this can be constructed by simply multiplying the policy by simply multiplying the policy to the first equation. So you will get mu of S multiply this policy pi A given S, and then you get this joint distribution of S and A from the initial distribution, and now I guess we can write that, and then we can unravel we can unwrap this P pi by rewriting it as the summation over A prime P pi S prime A prime and pi of A prime S prime, right? So this is the same as P pi of S prime, but notice that we are multiplying this pi of AS on both sides. So let's add this pi of AS here. So what does this give us? It gives us nu pi of SA is equal to nu pi of SA, mu pi of SA plus gamma and summation of S prime, summation of A prime, nu pi of SA, and then and then basically P pi S prime wait
is there a division pending mu chi?
Oh, I see what's going on. So this needs to be grouped with that, and this needs to be grouped with that, right? So once we group these two things together, we got S prime A prime, and then we have this S S comma A given S prime A prime. Okay, that's it. Right, so notice that this is pi of A prime S prime. I'm grouping this with this state occupancy measure, which gives us the V pi of S prime A prime, and I'm grouping this conditional with this this conditional together, so that it becomes the joint distribution of SA, right? Given as Yeah, that's right. By combining this and both of them conditioning on S prime A prime, then I get this this R SA by SA dimensional transition matrix. So both of these two things has a matrix form that we can write out. So so this is equal to mu plus gamma. Then this is P pi transpose nu of pi. Right. So down here, when we use this state action, when we use this state action occupancy measure, state action. So let me add this tilde here. So this is equal to mu of pi plus the gamma. Again, P pi tilde and tilde pi. Okay, so for completeness, I'm also adding the tilde here. So this P tilde is the same as this P tilde, and this P pi is the same as this P pi, right? So we see this very nice symmetry between occupancy measures and the value functions. So they're in some sense dual to each other, and then we'll see why this is the case, like just momentarily. But what this also tells us is that for both of these two things, we can write them as closed form solutions by just solving the linear system of equations, either involving inverting matrices of the form P pi inverse of R pi, or gamma P pi transpose inverse of the initial state distribution, right? So they're in some sense dual to each other, and the key difference is simply whether there is a transpose in when we use this state transitions and when we're solving this problem. Right. So there are quite a bit of mathematical beauty in Markov decision processes. Okay. So there's the another thing that we didn't actually solve, but we leveraged this fact in a proof last time. So I left this as a homework question. I left this as an exercise for you guys to work out. Work out this simple fact. But I think it's a good idea that we go over it because later we'll be using this anyways. Okay, so if this matrix I minus gamma P pi is invertible, then that means that in the previous equations and all these equations will give you like just one solutions, and it makes sense so the solution to this linear system of equations or these linear system of equations, they have unique solutions. Okay, so thanks to the gamma parameter being strictly smaller than 1, then we can actually prove that this is really the case. Otherwise, it doesn't make sense to write this inversion because this matrix may or may not be invertible in the first place. Okay, now let's prove that this matrix is actually invertible. Okay, how do we go with proving a matrix is invertible? So from the linear algebra courses, you've learned that so first of all, this is a square matrix. And the two linear systems of above are really just one being the transpose of the other. So it suffices to show that A is full rank, and then that's equivalent to say A transpose is full rank, right? So we only need to prove one theorem, and A is S by S or SA by SA, so it's a square matrix, so it makes sense to talk about invertibility. So if a matrix is full rank, that means that for any input X that then you apply this matrix as a transformation, X is 0 if and only if the output is 0 if and only if X is 0. Right. Therefore, if we can show that for all X that is not 0, then the output also is not 0. Then we have proven that this matrix is full rank. Right. So this is one of the ways that you can prove the rank of matrix being full rank from the operator linear operator point of view of matrices. Okay. So let's quickly go over this argument. So first of all, by the linearity of this, by the way, this I is identity matrix. identity matrix. So by linearity and then by triangular inequality, of this L infinity norm. So L infinity norm is a norm, so it's a metric, therefore it satisfies the triangular inequality. Okay, and once we have that, so how about the third inequality? So first of all, this requires us to look at what this P pi look like. So P pi is a transpose of a transition matrix. Therefore, every row of this P pi are probability distributions. So every row of P pi is a probability of S prime given S, right? So this is S, and all these values are probability of S prime to be 1, S prime to be 2, to S prime to be the cardinality of the state space, right? So what this is saying is that every row of this P pi matrix would add up to 1, right? Which means that this P pi transpose X is equal to, so let's calculate it coordinate by coordinate. 1 inner product with X, P pi 2 inner product with X, and we do it and we do everything this way. Then we can see that since this is a like addition, a non-negative addition of X, then it is always upper bounded by L infinity through the Holder's inequality. This is smaller than L1 norm of multiply with L infinity norm of X, smaller than L infinity norm of X. Since this is negative, then we can keep writing this equation. So this one checked. So finally, we just group everything together and notice that when the gamma is strictly smaller than 1, whenever X is non-zero, this is non-zero, right? So therefore the output is non-zero, therefore this matrix is full rank. Okay, I thought that was clear. So let's move on. So we've shown that it suffices to consider stationary policies, and then we talk about the Bellman equations corresponding to particular policy pi. So it turns out that the optimal value functions also satisfy a set of different Bellman equations called Bellman optimality equations. Okay, and instead of having an expectation, now we have a max, right? Converting from expectation to max. And instead of having a v pi function that's inside, we now have a v star function. So let me parse this Bellman optimality equation for you, right? So the optimal value function at S is the same as the as the one that chooses the best action that maximizes the summation of so this part is the expected immediate reward, and this part is discounted future reward. Discounted future reward by the optimal policy, right? So if this is the optimal policy already, everything in the future is optimal. So it suffices to choose A such that you maximizes the summation of the immediate reward and the future reward. Okay, so it's the same dynamic programming argument that's going on here. That we can all so intuitively like there's a formal proof in the textbook, but intuitively this is what the Bellman optimality equation is about. It's about like peeling the current layer out and then consider maximizing the immediate reward plus something that we leave unspecified as if you do everything perfectly in the future. So suppose you go backwards from the end of the day to the first step, then you can somehow keep back propagating this Bellman equations all the way towards the first step, and then you will know what is the right decision to make at the first step, right? So it's a dynamic dynamic programming, the same old dynamic programming that's going on here. Then in order to compute what this V star function is, it suffices to consider a system of nonlinear equations like this. So this is you have S equations here, and it's nonlinear because you have this maximization operator there. And then but if we can solve this nonlinear equations, then we are able to identify what this V star function is. And with V star function, it is easy to extract the optimal policy by simply converting it to the Q star function. Simply converting it to the Q star function and then take the argmax. Okay, so we'll get to how we can compute this V star and Q star function. But now I wanted to close a loose knot that we gave in the last lecture, because I told you that it suffices if we want to consider only the optimal policy. So there exists an optimal policy that is deterministic and stationary. So what I've shown you is that there exists a stationary optimal policy, but I didn't show you that there also exists a deterministic stationary policy. Okay, so now let's try applying what we know up to this point to formally prove this fact. Okay, first of all, given that we know that there is an optimal policy that is stationary, so let's say the pi star is stationary. Then we know that V star S is equal to V pi star of S. Okay, and because we know we now have this Bellman consistency, we have these Bellman equations, we can unwrap this by saying that now I'm drawing from this distribution given S, right? And then we can replace this as Q pi star function. Right, and this is obviously smaller than max of A Q pi star S A. Right, this is smaller than that. This is also since this one is optimal and stationary, this is also the same as the max of A Q star S and A. All right, so this is by the fact that this pi star function is optimal. Now we can define an alternative policy. Define pi star pi prime such that pi prime of S is equal to arg max of Q star SA. Right? We can always do that. So first of all, we can check that pi star is stationary, because it depends only on S and nothing else. And since this Q star is constructed with a stationary policy pi star in the first place, and also pi star is deterministic, right? Pi star is pi prime is also deterministic because we're taking the argmax. If there is a tie, then we can just break those ties arbitrarily, say by picking the one with that comes first, right? So it remains a deterministic policy. Right. So now, by definition, this V star pi is always smaller than V pi theta for any pi theta. Right. We can substitute pi theta to be this constructed pi prime. And let's see what we got, right? So on the other hand, on the right hand side, this is the same as Q pi theta as A S. And since this is stationary, this is further equal to V pi prime S. But we can substitute this to be y prime, like pi prime. Therefore, even though we have inequalities throughout, both the left-hand side and right-hand side are the same, right? So I can replace this with pi prime, which means that everything is equal, which means that this pi prime is also optimal. Okay, so I hope this argument is clear, right? So this is showing that so there exists an deterministic stationary optimum policy that is given by simply working with the Q star function, and the argmax of the Q star function gives us the optimal policy, at least one of the many optimal policies. Okay, so far we've shown that the crux of solving the Markov decision process planning problem is to construct this Q star function. And in the remainder of today's lecture, I'm going to talk about two different approaches of constructing this Q star function. So they're qualitatively different, but they're both very interesting to look at. The first idea is that, well, we can formulate this as a linear program, and then by solving this linear program, then we can get V star or Q star. And since we know that the entire family of linear program has polynomial time algorithms to solve them, then we know that solving Q star is computationally efficient. Another approach is another idea is to directly work with the Bellman equations and Bellman optimality equations, and then try to consider them as fixed point iterations, and then come up with some iterative algorithms to keep updating. Then we can prove the convergence of the sequence to the fixed point, right? So we'll talk about either approaches in the remainder of today's lecture. So maybe now it's a good idea. It's 2 o'clock. It's a good idea to take a 5 minutes break before we come back to the remainder of the lectures. All right, yeah, let's take a 5-minute break. Yeah, meanwhile, I'm around to answer questions. Yeah, if there are any slides that you found is unclear and wanted me to revisit, and I can just flip back to that slide and then answer those questions. And if you don't feel like unmuting yourself and speak up, you can also just type everything in the chat, and I can come back after my bio break. Yeah, I'll see you guys in a bit. 2:05. All right, it's 2:05. Welcome back, class. I didn't see any questions in the chat, so I assume everything's okay. Yeah, so please, I want feedbacks, and I need to know whether I'm going over the materials at the right pace, or whether I'm going over it too slowly that makes you boring, or I'm going over it too quickly that you need more time to digest. Yeah, so please like stop me when there anything that's unclear and ask me to clarify. Like sometimes I'm not looking at the chat box, but you can leave comments in the chat box, or just unmute yourself to stop me and stop me right there when you do not understand any of the arguments. All right, so we're going to be talking about how do we solve MDPs, solve the MDP planning problems, and then have some sense of the amount of computations that is needed as it depends on the parameters of the MDPs. Okay, so the first thing to talk about is the so-called linear programming approach that I believe dates back to I think 1990s, and yeah, I don't remember the exact year, but it's due to the Stanford professor. So the linear programming approaches of solving Markov decision processes tries to formulate the problem into the following like linear optimization problem subject to a set of linear inequality constraints. Okay, so what we are minimizing. So again, mu is the initial state distribution, and of course the initial state distribution, suppose we substitute the solution V star into this, we will get we will end up getting the substitute V equals to V star. We will get sum over mu s, and V star of s is equal to V star of mu, which is the optimal, optimal value. So how about the constraints? The constraints is really saying that V star is larger than the max of A R S A plus gamma S prime P S prime given S an A V S prime, right? So it is really a rewritten of this Bellman optimality equations by enumerating over all A. So notice that if you enumerate over all A and they satisfy this inequality, then you automatically satisfy this inequality. So what this constraint is saying that, so let's find the smallest possible upper bound of the right-hand side of the Bellman equation. And meanwhile, it needs to be self-consistent because the right-hand side also depends on V. So by replacing this nonlinear convex constraints into a sequence of linear constraints, linear inequality constraints, then you can make use of the linear programs with off-the-shelf tools to solve it. Okay, so the variables that we're minimizing over this V function, and V is in R to the S. And they satisfy this set of constraints, and this set of constraints carves out some kind of a weirdly shaped polytope. So this is a feasible region that's described in this. And we're minimizing this because we actually want to find the V such that all these are equal rather than the greater or equal to, right? And since we're minimizing this quantity, so it ensures that the optimal solution will always satisfy this is equal sign. Okay, so that's the intuition behind this this linear program, and it can be shown that the optimal solution to this linear program is exactly V star. Okay, so what makes it more interesting is when we derive the dual of the linear program. So like who has not taken a linear programming course before, or have no clue what mathematical programming is? Yeah, so typically like people who had undergraduate degrees in electrical engineering, mathematics, and computer science would encounter linear programs at least once in one of their courses. And this is just one of the instances and where you can reformulate the problem into a linear program. So the standard solvers for linear programs can be used to address this problem. All right. So what is interesting is that okay. So I've given a quick quiz here. So I hope that we can get some interactions over here. So let's say that we've solved this linear program and we've got V star. But in order to get the optimal policy, we actually need Q star. Can I get a volunteer to tell me how I can construct Q star from V star? Anyone? Right, so again, the optimal policy, as we've written, is equal to arg max of Q star. Anyone would like to give it a try?
All the stationary policies follow the Bellman consistency equation, and we find Q star from V star then.
Yeah, excellent. So we can basically just apply the Bellman optimality equation. So this is equal to max of A R of S A plus gamma summation of P S prime given S and A and then V star of S prime, right? So
no, there is no max over A.
Oh yeah, that's right. Thank you. Yeah, so by simply plugging in our knowledge of the reward and the transition kernels, then we can convert V star to Q star. And then that gives us the optimal policy. Okay, so again, so this is not yet reinforcement learning. So this is a Markov decision processes. We assume that we know the environment, we know the state transitions, and we also know the reward, right? So in this way, we can do whatever we want and then easily convert V star into Q star. It's not typically the case in the reinforcement learning setting where we do not know P or R as a function. Right? In that case, maybe it's better to solve the problem to directly solve the Q star function rather than working with V star. Okay, so like I said, the interesting part is when we derive the dual of that linear program, right? So there are several ways that you can do this. So first of all, you can just directly convert the primal into the standard canonical form of a linear program, in which case there's a standard formula for you to write down the dual for the corresponding maximization problem. Alternatively, you can formulate this as a general convex program and then follow by constructing the Lagrangian, minimizing the Lagrangian with respect to the primal variable, adding the dual variable corresponding. So in this case, the dual variable would be this new parameter. So I'm assigning one dual parameter for one inequality, for one linear inequality over here. And since these are inequality and we need complementary slackness, and that requires, due to feasibility condition, then this new parameter needs to be non-negative, which is good for us. And then the dual program will also have a set of linear equality identity equations, and these two things also give us some kind of a dual polytope, right? And which says that the new parameter that we're optimizing over needs to be within this convex set. So what is this new? So by just looking at this objective function value, we can already see that this new at the optimal solution is essentially the occupancy. It's essentially the occupancy corresponding to the optimal policy, right? So the optimal solution of this new is equal to nu pi star. Okay, convenient, right? And then for those who are familiar with optimization theory, you have this primal optimization problem, which tries to find the minimizer of the primal problem, and then you have a corresponding dual problem where you try to find the optimal solution by maximizing over a set of different parameters, and for linear program, and we know that this feasible region is feasible. There exists at least any policy, fixed policy satisfy this, so it is feasible. Therefore, by the Slater's condition, you can show that the linear program satisfy the so-called strong duality, which says that the minimum of the primal is equal to the max of the dual. The dual is over nu and primal is over v, right? These two are equal. And if we stare at it, this is completely intuitive, because what is this? This is a value of the policy, right? This is optimal value of the policy at mu. And if we look at this again at the optimal solution, when we substitute this v star into this, it also gives us the value of this pi star policy at mu, initial state distribution mu, right? So this is a underlying reason why we are seeing this a very nicely looking symmetry between the occupancy measure and the value functions, because they are indeed coming from the two sides of the same coin, which can be formalized using this linear program, the duality of the linear program. As an exercise, I encourage you to try deriving the dual by applying the standard Lagrange multiplier technique, minimizing the Lagrangian, and then constructing this exact formula, right? So it will be a very good exercise. I may well just leave this as one of the homework questions for you guys to work out. All right. So now there's this second quiz, right? So suppose now we instead of solving the primal problem, we are solving the dual problem, right? So it is just as easy to solve. It's the same old LP with the same number of constraints and simple the same number of variables. So once we had this new parameters, so new is state action occupancy is in R S times A. So how can we convert this solution to the policy? Anyone? So you don't have to have the full solution, but you can tell me the ideas that you may have. Anyone wanted to speak up? Okay, yeah, I'll just review the answer. So let's say that this new star SA, this is equal to new pi star of SA, right? And this is like the joint distribution, even though it is not a probability distribution because we're summing over the individual trajectories without normalizing it, but we could normalize it into a distribution. It has the same form as that of the joint distribution, in the sense that we can rewrite this as the state occupancy multiply with pi of pi of A given S, pi star of A given S. So what you can do is really to normalize this. It's really to normalize this you can construct pi star, since this is a distribution, by using nu pi star SA divided by the summation of nu pi star of SA, where we sum up all the A's. So that will give you the optimal policy by solving the dual problem and then constructing the policy from the dual optimal solution. Okay, so it's not unclear. It's not clear that this will necessarily give you the optimal the deterministic policy, but yeah, it will always give you an optimal policy. Yeah, and when the optimal solution is unique, then it will always give you the deterministic optimal, deterministic and stationary policy. Right. So this was one of the confusions from the last lecture. And how do we connect the policies to occupancy measures? All right, so we finished talking about linear programs and the linear programs approaches. We'll talk about these computational properties later. But for those who are familiar with linear programs, from an undergraduate course, you might have worked out the tabloid type of pivoting and then solving the simplex methods so that's a very practical solver for it, but unfortunately not really polynomial time in the worst case. There are polynomial time solver for linear programs called the interior point methods. If you wanted to learn more about that, you feel free to check out my course last year when I talked about the convex optimization, which I talk about the primal dual interior point methods and how you can solve a general convex program in polynomial time. Okay, so now let's move to the second idea of solving Markov decision processes, right? So we already know that the MDPs are governed by this set of Bellman equations. So we've formally derived this. You can manipulate this and then convert this into the Q functions Bellman equation like this. So this will be the Q functions Bellman equation by simply taking the thing in the middle, strip out this max x and replace this V star with Q star, but with a maximization over A prime. Okay, so it can be well, for convenience, let's define this nonlinear operator, right? So this Q is operator. So an operator takes a function and output another function. So that's what an operator is. And this is nonlinear operator because it's not linear due to this maximization. All right, so how do we formally write it down is by defining this VQ with a subscript Q that encodes this nonlinearity, and everything else becomes a linear transformation based on this transition kernel transpose plus this reward vector. Okay, so the key idea is that you take this Q as an input, and then it gives you a Q prime. It gives you a different Q function. So it can be shown using a lot of things we've already covered that it can be shown. So feel free to read the proof of this theorem. So it will be very easy to read now. So Q is equal to Q star if and only if this Q satisfy this Bellman optimality equations. All right, so the first algorithm that we'll talk about in this iterative setting is so-called value iterations. So it works very easily. So you basically initialize this Q0 arbitrarily, right? So you can initialize this arbitrarily, and then you say for instance you can simply set Q0 to be 0 everywhere. That would be a valid initialization, and then you iteratively apply this Bellman optimality operator and keep updating this Q, right? You run that for k times and you take k to infinity. And the idea is that at the end of the day, the limit of this sequence will give you Q star. All right, so I hope that's a simple enough an algorithm. So whenever we look at this kind of a iterative algorithm, what is the right theoretical question to ask here? We can potentially ask, like, does it converge at all? So it's a limit of k goes to infinity, qi, I guess qk, is it equal to q star, right? So this is a question that we can ask. We can also ask, what is L infinity difference between q and q star as a function of k, right? So this will be the rate of convergence. How quickly in the finite time and finite iterations does q of k get close to the limit point, right? So that's the first. The second question, we can like ask the second question in a slightly different way in terms of the iteration complexity. Which says that, like, given epsilon as an input, how large does k needs to be? K is larger than some complexity measure of some function that depends on epsilon, right? So can we say that if we take epsilon as an input, and this is the number of iterations that I can set in this algorithm for me to obtain an epsilon optimal solution. So it's a flip side of the second question. So now let's analyze the convergence of value iterations. Okay, so the first observation is that the Bellman operator is actually the so-called a gamma contraction. Gamma contraction. So by gamma contraction, what's going on? Is my Apple Pencil out of battery? That would be really, really bad. So let me try it again. Oh, shit. Gosh. Yeah, so let me maybe try explaining this without using my Apple Pencil, and I'll make sure that I send you guys the make sure that I send you guys the notes after the lecture. So the idea is that once we apply this Bellman operator, then this q minus q prime that will the difference between any two vectors will always get smaller, and the extent to which it gets smaller is like exponential. So notice that gamma is strictly smaller than 1. So if we keep applying the same Bellman operator and then substitute this q prime to be q star, and then the first q to be our initialization, and repeatedly apply this, you will end up getting a sequence that converges to 0. And when it converges to 0, it indicates that the L infinity norm of qk minus q star is going to get smaller exponentially as k increases. Okay, yeah, I'm meant to prove this, but awesome, it suddenly starts to work. Good. I don't know what's going on, but so let's prove this. So we'll start from the left-hand side, the tau q minus tau q prime infinity. So this is by simply plugging the Bellman optimality equation. So recall that this is equal to r plus gamma and p times vq, right? And also vq is equal to max of q 8, right? So this is a Bellman operator. So since we are taking the difference, then our term got canceled out, right? Because it doesn't depend on q at all. So we can write this to be gamma L infinity norm of P VQ minus P of VQ prime, right? And now since P is a linear operator, we can group them together. We get P of VQ minus VQ prime infinity. Okay, so what is this P? So again, this P is this matrix where every row is a probability distribution. So every row would add up to 1. Every row would add up to 1, right? So we've already seen this from the previous analysis of that invertibility of that matrix, that this P matrix satisfy the property that when we apply anything vector into this after the P, then it always gets smaller, right? It always gets smaller in terms of L infinity norm bound. So we can maybe let me wrap around. So we can bound this to be VQ minus VQ prime L infinity norm, right? So this is by applying the operator norm of P in L infinity, right? Which can be more easily calculated by simply consider every row of this matrix P to be to sum to 1, and then work this out coordinate wise for every element of this vector. Okay, so now like I guess by applying the definition of L infinity norm, then we get VQ of S minus VQ prime of S, right? So this is just by the definition of L infinity norm. And well, so now there's a slightly tricky part we need to discuss. Discuss if VQS I guess if VQS is larger than VQ prime S, larger or equal to VQ, then we can get rid of this absolute value, right? So we'll discuss this case first, then gamma max of, yeah, I guess for those S, right? For each X, they might not satisfy the same ordering for the same S, but well, we can for each S we can discuss whether this one is larger or that one is larger, right? So under this condition, we can get VQ of S minus VQ of VQ prime of S, right? So let's take A to be arg max of Q S A. Okay, let's take A to be arg max. Then we can rewrite this of the gamma max of gamma of I guess the Q function Q of S A. Yeah, I'm just substituting this A into this to be the arg max. Subtract. So I'm making the larger one larger and making the smaller one smaller by subtracting the max of A VQ prime. VQ prime S is just the Q prime of S of A, right? So I can write this inequality. This inequality by making the larger one larger and making the smaller one smaller. By making the negative one even more negative. So this is always upper bounded by this quantity, right? And now since this is arc, since this is a largest, then I see. Yeah. So So this is actually the definition of VQ of S. I'm not changing anything. I'm only making the first term larger. I'm only making the first term larger, but the second one remain where it is. And now I can replace this by the argmax. I can replace this with SA minus the Q prime of S and A. Now I'm substituting this particular A into this Q prime, which always makes this always makes this larger. Right, and then this is smaller than gamma of absolute value Q of S and A minus Q prime of S and A. Right. So notice that this is symmetric. So when I replace this with the other side, then all the same argument would follow through for the other direction. So for all pairs of S and A, for all pairs of S, I can bound this using using this inequality, which says that, well, by plugging into the above, which gives us a gamma of max S and A Q of S A minus Q prime of S and A, absolute value. And now what remains is to just look at the left hand side and right hand side, right? So the left hand side is here, and the right hand side is gamma, and by definition recovers the right hand side of this inequality. Yeah, I hope it was clear, right? So I didn't explain this part well initially, but yeah, so this is by simply applying the definition of VQ prime. Okay, now with the Bellman operator, we've shown that the Bellman operator is a gamma contraction, and then we can try iteratively apply this lemma. So tau of Q minus tau of Q prime, L infinity norm, smaller than gamma of Q minus Q prime, L infinity norm. And by substituting Q prime to be Q star, and by taking Q iteratively, then we can write Q of QK minus Q star. So this is the this is smaller than gamma of so first of all, this is equal to tau Q K plus minus 1 minus Q star. And notice that Q star is a fixed point, right? Therefore, tau of Q star is equal to Q star. So then, and this is smaller than gamma of Q K minus 1 minus Q star. So initially, so Q0 minus Q star, so this thing is bounded, is smaller than 1. Right? Why is it? Because we are, yeah, actually it is smaller than 1 over 1 minus gamma. Yeah, why is that? And this is because we assume that the reward vector is always smaller than 1 or larger than 0. And the summation of all the discounted reward vector t minus 1 from 1 to infinity of R S of A for any S of A, so this is always smaller than 1 over 1 minus gamma. So no matter what we do, so these two functions are always always the difference of these two functions are always smaller than 1 over 1 minus gamma. Therefore, by chaining all this inequality together, we get gamma to the power of K multiply with 1 over 1 minus gamma. Yeah, and this is equal to 1 minus gamma to the power of K minus 1 minus gamma. So remember, so how do we simplify this even further? So this is already geometric convergence, but maybe we want to write it down in a more simpler manner. So recall that there's this inequality, there's this thing that you should be familiar with. So if you take limit n goes to infinity, then you get e to the power of -1. Right, so we can apply this here, and in fact there's also there's also a bound that this is smaller than e to the power of -1 for all n larger than 1, all n larger than 1. So so we can simply apply this and then rewrite this into 1 minus gamma. I guess e to the power of minus k over 1 minus gamma. Yeah, sorry, it's 1 minus gamma times k. Right. So by just applying this inequality, then we can simplify it into something that goes to 0 at this particular rate as k goes to infinity geometrically. All right. So the next thing that I want us to do is how do we convert this iteration complexity into the how do we convert the convergence bound of this quantity into the iteration complexity. So this is really straightforward. So you basically set this this epsilon to be equal to 1 minus gamma e to the power of minus 1 minus gamma to the power of k, and then try inverting it by so this is the same as setting k to be setting k to be log 1 over epsilon 1 minus gamma divided by 1 minus gamma, right? So that will be the iteration complexity for getting qk to be close to q star in L infinity norm. And the last thing that we need to do for the value iteration is to convert the L infinity norm bounds of the q star value function to the suboptimality in the policies, right? So we can construct pi q to be arg max of q SA over A, right? So we can construct this policy pi q. The question is that how can we get a suboptimality bound of pi q, right? So it turns out that you can bound the suboptimality using how close that your q function is close to the q star function in L infinity norm bound, but there is a slight loss in terms of the parameters by this 1 over 1 by this factor of 1 over 1 minus gamma. So notice that gamma is usually close to 1, say 0.99. So this is like 100 times or more amplification of the error. Yeah, so that's why it's called Q error amplification. So this bound in some specialized cases can be improved, in which case you do not lose this factor of 1 over 1 minus gamma. So we're not going to be talking about that today. So hopefully in one of the advanced topics we'll be talking about how we can get rid of this factor because it is useful when we work with reinforcement learning and we need tighter bounds in some cases under additional assumptions, right? So I'm gonna skip this proof. Like you should read it. It's pretty straightforward. So basically adding or removing stuffs and then bounding each part separately using L infinity norm bound, and then the entire argument would just follow through. So the interesting part is at the very end, right? So at the very end, you decompose things into Q, the approximation error of Q and the approximation error of what you are trying to bound in the first place. So notice that both the left-hand side and the right-hand side depends on V star minus V pi Q, right? So by simply taking the L infinity norm bound on both sides and move this to the left-hand side and then divide both sides by 1 minus gamma, you recover this type of bound, right? So it's like you're bounding the left-hand side using itself, and then that introduces an additional factor of 1/1 minus gamma. Yeah, so I encourage you to read this proof with more details after the lecture. So we're coming towards the end, but I wanted to just quickly mention that the value iteration is not the only iterative algorithm that's out there for simulating the Bellman equations. So value iterations aims at simulating the Bellman optimality equations, but you could alternatively make use of this closed form solution that we've learned, right? We've learned that we've learned that this QPi function satisfy this closed form solution, the gamma of p pi multiply with reward multiply with reward, right? So with this closed form solution to the standard Bellman equation for policy pi, then you can run the so-called policy iteration algorithm. So the policy iteration algorithm works as follows. The alternatively run policy evaluation and policy improvement. So by policy evaluation is essentially solving this linear system to get this Q pi k, and then policy improvement involves involves making use of this Q pi k and then find the next policy to be the greedy policy corresponding to this current iterate of Q pi k. Okay, and it can be shown that with a similar number of iterations, then you can get a epsilon optimal. You can get an epsilon optimal policy. Okay, I'm gonna skip the proof. And to conclude the lecture, I wanted to comment on the computational complexity of these MDP solvers. We'll start with value iteration. So we've seen that it takes log 1/1 minus gamma epsilon, and due to that error amplification, now you have this 1 minus gamma square over 1 minus gamma. So you need this many iterations. So how about every iteration? So in every iteration, the time complexity that you need is proportional to the square of the state space multiplied with A. So this is really the application of apply the Bellman optimality operator, right? So that's a sample complexity. That's the iteration complexity to get the epsilon accurate solution. On the other hand, like it doesn't really allow you to choose epsilon to be 0, right? So you cannot choose epsilon to be 0, otherwise it could take forever to converge. So it doesn't really give you the exact solution. And similarly for the policy iteration from the lemma that we've seen just now, you can rewrite it with an iteration complexity to be this over 1 minus gamma. But the time complexity for solving the policy evaluation part, if you do it naively, would be to invert a matrix as SA by SA, right? So that would be SA cube. But this can be improved over to S cube plus S square A by solving the closed form solution for V pi rather than for Q pi directly. Right, so then you will only have to invert a matrix of S by S, which takes S cube, worst case time complexity, and after that you apply the Bellman equation, which takes S square A, and that gives you the per iteration time complexity for policy iteration. So the linear program is more complex in general. So you'll take the polynomial number in terms of the state space and action spaces, but the benefit of using the LP is that it's able to give you the so-called strongly polynomial time algorithm that gives you a computational bound that's completely independent to epsilon. So you can really set epsilon to be 0 without actually like changing the fact that this LP is a polynomial time algorithm. So all these computational results that I'm not going deeper into is summarized in this table, and this L is like machine precision. So if you only want to get to a solution that satisfies this machine precision, then well, the value iterations and policy iterations are good enough. And then otherwise you need to use LP and incur like additional polynomial dependency in state space and action spaces. And what is interesting is that in general, so the policy iteration, like policy iteration can be interpreted from the LP perspective. So this is a version of the simplex method. So in general, simplex method is not strongly polynomial. On the other hand, for this special case, it can be shown that the policy iteration actually converges, and you can come up with bounds that's independent to that epsilon parameter for policy iteration with a more involved analysis. Okay, so that's what I'm gonna where I'm gonna stop today. So we've talked about most practically relevant algorithms for solving the MDP inference problem. And the thing that I wanted to point out that it depends on polynomially in the state space and action spaces, and in the best algorithm actually already depends on S squared, right? Which is bad because often the number S is astronomical, and computationally it is impossible to solve large MDPs exactly based on this observation. So in the next lecture, we'll talk about approximate and randomized algorithms for solving MDPs, and hopefully we can further improve over these computational complexity bounds. And then that will get us closer to the reinforcement learning setting where we actually got samples of the transitions rather than observing the exact transitions. All right, yeah, so that's the end of today's lecture, and thank you very much for coming. So I don't have an office hour officially, so I'm gonna just stay for another half an hour in case any one of you wanted to chat about the lecture, about anything like related or unrelated. So I guess next half an hour would be like my office hour this week. Yeah, thank you all.